good warm-up problem for today. Mr. Linsmeyer's accountant is figuring a depreciation rate of 5% per year on a farm tractor that tills the bean fields, which just happened the other day. If the tractor was worth $192,000 new, what is the value on paper 14 years later? So, again, we will be using from yesterday the that formula, or which is basically the same as, I think we had it like P of T equals P sub 0 times 1 plus or minus, nope, we said R yesterday, or plus or minus 4 to the T. No, it's better. For you, T. Alright, so we're looking for a value. Anybody get one yet? What do you got?
I got $93,633.59.
59 cents? I got 60. Wow. We're fighting over a penny.
I guess actually.
Penny
I
is
didn't
a
round
lot.
it right.
Penny's a lot. Yep. Okay. All right. So that's what I got too. So we're right there. So we're at, so using this one right here, so that would be then 192,000 times 1. Am I going to go plus or minus my R? Minus, because it's depreciating in value. The rate then was 5%, and we went for 14 years. Okay. So that's 192,000 times 0.95. Power, which then gets me $93,633.60. 0.595. Questions on that? Today we're going to introduce you to a new type of growth or decay function, okay? And that is called a logistic growth or logistic decay function. Okay? Now, an exponential growth function would continue to grow and grow and grow and grow forever. Correct? Okay? But there's a problem with that. For instance, let's take population. Population has for years been considered exponentially growing. The more people that are on planet Earth, then they have babies, and then there's more people, and then there's more people, and there's more people. You know, it's an exponential growth problem, right? What's the problem with an unrestricted exponential growth problem in terms of growth population? Any problems with it? What do you got? Okay, not enough resources for one. What about space? We have a lot of it yet, but if we continue to keep growing, right, we're going to run out of space. Right? Or if we think back to the population growths that we had like yesterday in, was it San Jose and Columbus, were the two examples? Okay? They're going to run out of space because they're going to run into the next town and kind of, you know what I mean? Cities can only grow so big. Okay? Okay? So, in many growth situations, there is what is called a limit to growth. Okay? Every minute we could double the size of this room, right? Or double the number of people in this room, right? But what's going to end up happening? We're gonna end up with no space for anybody. We're not going to be able to add people into the room anymore. So there's a limit to the amount of people we can fit in this room. A plant or a tree will only grow so tall. Population of a city won't grow exponentially forever. Sales of a new product will actually end up to taper off as we go along. Okay? In these situations, growth begins in an exponential manner, but eventually it slows and it levels up. And we call these logistic functions. Okay? A logistic function starts out and it grows exponentially, but then it levels off and it doesn't grow past its limit. Now, let me take one step back. An exponential function has a horizontal asymptote, and that's the bottom, right? It doesn't go any lower than that. Okay? A logistic function, yes, still has its lower limit horizontal asymptote. Okay? So if I went like this, now you're looking at an exponential function, like you've seen before, right? Okay? Okay? A logistic function has an upper horizontal asymptote also. And that upper horizontal asymptote is called the limit to growth. The function will never get bigger than that. So it's tunneled in. Okay? So the function will always only exist between the green and the purple. It will never go outside of green purple. Let's take a look at a couple of different styles of logistic growth functions. Okay? So here are the two styles of logistic growth functions. On the left, we have just a regular, basic, exponential base. Okay? So it's C, which is our limit to growth, over 1 plus a times b to the x power. A times b to the x power is the exponential part of it. That's where the exponential part comes from. But then it grows faster than the c, and then that's where the leveling off part is. So A, B, C, and K, we'll get to K in a minute, are all positive constants. And B, here's the kicker, B is less than, or I should say between 0 and 1. So it's an exponential decay, which creates a logistical growth. Let's see if I can, this one, this one. An example of what one of these might look like would be f of x equals 100 over 1 plus 2 times 1/3 to the x power. That's just an example of logistic function, where the upper limit, the limit to growth, would be 100. So we'd have a horizontal asymptote up at 100. We'd have a horizontal asymptote at 0. Okay? In a more fluid, because we're using E, and E is more for like a continuous growth type thing. Okay? C over 1 plus A times E to the negative kx. Now it says that k is greater than 0, but that's just because it's got to be that way because that exponent there has to be negative. X1 has to be negative because that denominator needs to be a decay function. Okay. Conversely, okay, if b is bigger than 1, then it's logistic decay, or if k is less than 0, then it's logistic. And so then instead of exponentially growing and reaching the upper limit, we would start at the upper limit, exponentially decay, and then level off at our lower. All right, here we go. So we want to find a logistic function with the following conditions. We have an initial value of 12. That means we go through the point 0, 12. We have a limit to growth of 60. And our logistic function passes through the point 1, 24. Okay? So for purposes of today, we're going to go f of x equals c times 1 plus a b to the x power. That's the form that we wanted. Okay? So, based off of your notes that you just took, is there anything that I can fill in on this f of x equals c times 1 plus ab?
Yeah.
Okay. So what is that?
60.
And what part of the formula is that?
C.
C. Okay. So my function is already going to be f of x equals, and 60 is going to go up top. So I know that right from the start based off of my limit to growth is 60. Okay. What else can we figure out? Do we agree that 12 is A? Yes? Yes? 100% agree 12 is A? I don't. I'm looking more at this part right there. That's a point that it goes through, right? So what would 12 be? The f of x part. Okay? 12 is the f of x part. What other part can I fill in? The x is 0. B to the 0 power. 1 times A. So this is just 12 equals 60 over 1 plus A. How do you want to solve that? Multiply both sides by 1 plus A. Then what? Do we agree with subtract 12 from both sides? Do I need to distribute? What can I do instead? I can divide both sides by 12. I'm going to divide both sides by 12. Now I subtract 1. So I get A is 4. Okay. So now my function becomes that, right? So we've used 2 of the 3 things that we were given. So what do you think we should do now? Okay, the third thing, right? Okay, so what's going to go where? Okay, so we're going to have 24 here equaling 60 over 1 plus 4b to the first power. Now what? One plus 4b on both sides? I'm out of color, so we'll go black. So 24 times 1 plus 4b equals 60. Then what? Divided by 24. So that's 1 plus 4b equals 5 halves. Subtract 1. Subtracting 1 is the same as subtracting 2 halves. So that's 4b equals 3 halves. Dividing by 4 is the same as multiplying by 1/4, right? So that gives me b is 3/8. Okay? So our function, f of x, is going to equal 60, that's our limit to growth, over 1 plus 4 times 3/8 to the x power. Quickly, I'll show you the graph of it. Okay. So I would start with a fraction, because we have a fraction. 60 was our numerator. 1 plus 4 times, and then I would open up a set of parentheses. My fraction was 3. Oops, my fraction was 3/8, and that is being taken to the x power. Now, I can hit enter. There it is. There's the start. We don't see the whole thing. Okay? So let's pull our window back out a little bit, and let's expose it a little bit. -10, I'm okay with that. Whoa, hang on. That's not bad. Menu, window, settings. That one. Let's go 100, because we can. Minimum. Let's go -10. Here we need to go up to at least 60. So I'm going to go 80. And there is our logistic function. Starts out, grows exponentially, and then levels off. It comes back to us. You try one on your own. All right, so you should have gotten f of x equals 30 over 1 plus 5 times the third root of 1/5 to the x power.
If we wrote out the decimal version.
0.5848. Yep. Which would have been, so this would have been 30 over 1 plus. The 5 would still stay out there. It can't be 5.58. You know what I mean? And you can't distribute that in.